Hey there. This next podcast is about rotary motion, which is something a little bit different from what we've been doing. It doesn't involve solving equations or graphing sinusoids or any of that. In fact, it doesn't involve sine or cosine or tangent at all, which is kind of a nice break. But what it is about is it's related to the idea of a radian pretty intimately. What rotary motion problems are about is about objects that are spinning. So like a wheel or a Ferris wheel or a uh, gear or a pulley or any of those things. Rotary motion are the problems in rotary motion are describing the what's going on with those things that are spinning. So how fast is it spinning in angles per time? How fast is an object on the thing that's spinning actually moving in meters per time or miles per time or something like that? So there's a number of different things that we kind of have to keep track of with rotary motion, but we're going to start by going all the way back to the idea of what a radian is. So you remember that when we first learned about the definition of a radian and saying, okay, it's this new unit, and the big idea of the unit is that if I look at the radius r, we're going to start with a radius of 1 here, that if I go that same distance, if I were to take a string and measure out that same distance along the edge of the circle, right, that would be 1 radian, right, 1 radian. And radian is a measure of angle, right? But this arc length here on the unit circle is 1. So we define on the unit circle, the number of radians is the same as the measure of the arc length. But that's only because the unit circle has a radius of 1. If I had a bigger circle, let's say that down this big circle here, that the radius is 3, and I were still to measure out 1 radian, right? The arc length on the unit circle of 1 radian is 3, but on this bigger circle, the radius is actually going to be 3 times 1, which is 3 radians, right? If I were to measure at a different angle, let's do on the same 3 radius circle, let's say that this is, this angle is 2.13 radians, then this arc associated with the 2.13 radians would be 2.13 times 3, which would be 6.39 units. So in general, right, to figure out the arc length, I could say the arc length is radians, or radius, times radians. Now, this only works if the angle is in radians. It doesn't make any sense to say the arc length is the radius times the angle and the number of degrees. But, this is all really hinged on the definition of radians. I'm going to use symbols now to write the same equation. I'm going to use x to represent arc length because it's a distance. I'm just going to write over here distance. I'm going to let radius be r, that's kind of obvious. And then radians, I'm going to let be theta. I know that we've been using this convention that theta is in degrees and x is in radians, but you can see that this is kind of confusing here because I have another measure that we're going to be using for x, which is distance. And this is angle in radians. Okay, so hopefully you're starting to see how this could potentially be helpful if I'm thinking about something that is spinning. So now let's look at this here, units or circle with radius 3 and think about it as a wheel, right? So let's say that I want to move this wheel forward 3 feet. And let's say that the radius of the circle is 3 feet. And I say, well, how many radians would the wheel need to turn in order to move the wheel forward 3 feet? Well, I would need to move it through 1 radian because that is the arc length. That's how far the edge of the wheel is going to move, right? As I go 3 feet, I want my arc length to be 3, which corresponds to a radian of 1. This is really not the most useful and most helpful idea about rotary motion, though this is kind of fundamentally where we're going to start. What's really interesting is what happens when I start thinking, instead of distances and angles, if I think about velocities. So what that means is, let's look at what happens if I take these two sides of the equation. I divide them both by t. Okay, so the left side is just distance over time, which you guys are used to thinking about distance over time as being, how far I go divided by how long it takes me to go. That's a speed, right? What we're going to call this is we're going to use this kind of curly V, right? It's not just a regular V. It's kind of sideways. This is the Greek letter nu. I know you're going to call it v, but I'm going to call it nu. Nu is what we're going to call the linear velocity. Now, it's just like every other velocity that you've ever met in your life. It's about how fast something's going. So if I'm running 3 miles an hour, my linear velocity is 3 miles an hour. Now, on the right-hand side, this is where the interesting part of this equation goes, right? So I can rewrite this. I can pull the r out of the fraction and say that this is the same thing as r times theta over t. Okay, now that is the radius times the angle in radians per time. Now what that is called is the angular velocity, angle per time. And actually, I'm going to rewrite the equation one more time using the symbol for angular velocity, which is kind of this curly W, and this is the Greek letter omega. Those of you who are familiar with fraternity houses are probably like, that's not an omega, it's a lowercase omega. That's why it doesn't look familiar. And this is the angular velocity. So what angular velocity measures is angle per time. So just to give you kind of a qualitative understanding of what the difference between linear velocity and angular velocity is thinking about the idea of somebody on a merry-go-round. Okay, so I'm going to do something a little crazy to help you understand this. We're going to look at this video of these random kids on a merry-go-round. Whoa, there they go. Okay, do you everybody remember this kind of merry-go-round from your childhood? Okay, we're going to pause it and talk about it. Now, these people are all spinning at the same angular momentum because they're all sitting at the same on the same merry-go-round, and that merry-go-round is rotating all as a unit, and they're all spinning at the same angle per time. It doesn't really matter who's sitting further in or who's sitting further out, right? They're all spinning as a unit. If somebody was sitting in the middle, they would still be spinning at the same angular momentum, or not angular momentum, angular velocity, excuse me. So they'd be sitting in the middle, they'd be spinning at the same rate, the same angle per time. Because if they were sitting in the middle, say facing this kid in the yellow shirt, right? Like as he goes around, he's still going to be facing that guy, right? He's still rotating at the same rate. But you know, he might not be going very fast. Obviously, there's a kid sitting at the middle facing kid in the yellow shirt, right? The kid in the yellow shirt is spinning really, really fast and like about to get thrown off because he's going so fast, whereas the kid in the middle is just rotating and kind of has a boring seat. So the difference between these two kid situations is linear velocity, not angular velocity. The kid in the middle and the kid on the edge have the same angular velocity, but the kid on the edge has a big linear velocity and the kid in the middle has very little at all. Okay. Um, Okay, so let's go back to our actual math. So we have this here equation, okay? Nu equals r omega, right? Which is going to be hugely important in doing these types of problems. Nu is the linear velocity, r is the radius, and omega is the angular velocity in radians per time, right? Because remember, this whole thing that we've been doing has all been dependent on the idea of the definition of a radian. So this is not going to work if I have my angular velocity in anything but radians per time. Okay, so I think the best way to proceed with this is we're going to take a look at a specific problem. Okay, so here we go. Let's read through the problem. The propeller on a freighter has a radius of about 4 feet, and there's this picture. At full speed, the propeller turns at 150 revolutions per minute. So before we even think about what the question is asking us, I want to, one, if I didn't have a picture, I would want to draw a picture. Two, I want to label this picture, right? So what is 4 feet? Well, it's the radius. It's this distance here is 4 feet. Okay. And then the other thing is I want to figure out what this information that I have here. So 150 revolutions per minute. What is a revolution per minute? Is that an angular velocity or is that a linear velocity? So that really hinges on what does a revolution measure? Is it a measure of angle or is it a measure of distance? Well, it's a measure of angle, right? A revolution is a complete turn. So it's saying that, one revolution is a certain number of, spinning that I've done, how many I have per minute. So this is an example of an angular velocity because it is angle per time. Okay, so let's just take a look at what we have. We're being asked for the rest of this problem. Okay, what is the angular velocity of the propeller in radians per second at the tip of the blade and at the center of the propeller? Okay, so we've confirmed that I have an angular velocity, right? So now what this question is saying is give you the angular velocity, but give it in radians per second as opposed to revolutions per minute. So we have to convert this 150 revolutions per minute to radians per second. So all we're doing is changing units. We don't have to use that equation. All we have to do is do, a t-chart or stoichiometry, whatever you called it in chemistry. What we have to do is get from revolutions per minute to radians per second. So what I'm going to do is I'm going to multiply by a factor that is two equivalent angles that gets rid of revolutions and brings in radians, right? So I want to have revolutions in the denominator because that's going to cancel out, and I want to have radians in the numerator. So let's think about that. How many radians are there per revolution? Well, all the way around a circle is 2 pi radians, which is also 1 revolution. Great, that's my conversion factor for radians to revolutions. And the other thing I need to do is I need to get rid of minutes and I need to bring in seconds. So I'm going to multiply by another factor, which has minutes in the top and seconds in the bottom because I want to get rid of minutes and I want to have seconds. So let's think about how many minutes are equivalent to how many seconds. Well, 1 minute is the same thing as 60 seconds. Sweet. So now all I have to do is actually do this calculation. So let me pull up a calculator. Okay, so let's take a look at this. To do this calculation, I just need to multiply across the top and multiply across the bottom. So I'm going to have 150 times 2 pi times 1, which is just 1, divided by 1 times 60, so divided by 60. Okay, so this comes out to be 15, ooh, whoa, let's try that again. 15.70, and then the units that I'm left with, the revolutions canceled, the minutes canceled, and what I'm left with is radians per second. Great. Okay, so that is what I did. So now the question is, like, if I read this part A again, I'm looking for the angular velocity at the tip of the blades and also at the center of the propeller. So what's the difference between those two? And this is kind of a trick question. The angular velocity, remember when we looked at the kids on the merry-go-round, every kid on the merry-go-round had the same angular velocity because the merry-go-round was moving as one big unit. So unless the middle of this propeller is spinning faster than the edges, which doesn't make any sense, right? Like it has to rotate as one big unit. This is the angular velocity everywhere, right? At the center and also at the tip. Okay. So part B, on B. What is the linear velocity in feet per second at the tip of the blades? Okay, so I have an angular velocity, and now I need linear velocity. So that's telling me that I need to go back and I look at my important equation, nu equals r omega. So I'm going to go back and I am going to write my new equation, nu equals r omega. Let me get rid of this little thing. It's kind of in the way. So nu equals r omega is the thing that relates the linear velocity, remember, is this, and this is the angular. And remember, the angular velocity always has to be in radians per time. Good news, we have an angular velocity in radians per time, so we can just use that one. So I get the linear velocity is equal to the radius, which in this case is 4 feet, times the angular velocity, which is 15.70 radians per second. Now you notice that I have my units in the middle of this problem. I would totally recommend that you do that because that way it's going to kind of keep you honest about whether or not you're doing the problem in the way that you're supposed to. So I'm going to do 4 times 1570 again, pull up my calculator. So times 4, and I get 62.83. So going back to my presentation, nu equals 62.83. And then let's look at the units in the problem to figure out what the units of the answer are. I get feet radians per second. Now, I wanted to know the answer in feet per second, right? So what's with this radians in the middle of what's going on here? Well, what's going on is that radians is kind of a fake unit. If I go back and I look at my oh, I just screwed something up with my presentation. That's okay. If I go back and I look at this, right, number of radians is defined as the arc length over the radius. Now, if I think about the units of what's going on here, right, the arc length is a length. It's going to be like centimeters or, feet or something like that. And same with radius, right? It's going to, if they have to be in the same units, if I divide centimeters by centimeters, I have nothing left, right? So radians are really like an unit, right? They're not regular units. They're actually a ratio of lengths, right? So really, this is what's kind of cool. Oh, I erased that 16 or 63. Nu is equal to 63 point something. Radians really is not, it can just kind of appear or disappear at will out of these equations, unlike any other unit in the history of time. So I had 63 point whatever, 83. and it was feet radians per second, but really it's just feet per second because radians can appear or disappear at will. Now, that's specific to the fact that all of this was about the definition of radian was where it always started for. Degrees can't disappear at will, revolutions can't disappear at will, just radians. Okay, and then so let's look at the last bit of this question. Is this at the tip of the blades or is this at the center of the propeller? Well, linear velocity does matter where you are on the rotating object. So this is, I said the radius was 4, right? So this is at the tip because I'm looking at a radius of 4 out from the middle. Now at the center, r is equal to 0, right? So my whole linear velocity is going to be, the linear velocity is 0 times whatever the angular velocity is. So that just tells me that the linear velocity is 0. Okay, that's it for today.